Bien, muy buenos días. En nombre de la Universidad Técnica de Manabí, de la Facultad de Ingeniería y Ciencias Aplicadas, le damos la más cordial bienvenida a este nuevo espacio de conferencias magistrales en el marco de nuestro octavo Congreso Internacional de Ingeniería Aplicada, que se celebra en el marco de nuestra novena Convención Internacional, Científica Internacional, perdón, de la Universidad Técnica de Manabí 2025. Es para nosotros un placer contar en la mañana de hoy con el doctor Rajeev Singla de la India y actualmente trabaja en la para el Hospital Occidental de la Universidad de Sichuan en China, quien nos trae una interesante disertación. Saludamos a toda la audiencia presente en esta sala Zoom, así como a quienes nos siguen por nuestros canales en las redes sociales de Facebook Live y YouTube. Bien, good morning, Mr. Rajeev. Good morning from Ecuador and good night for you in China. Thank you for agreeing to attend our conference. It is a great honor for us to have you as a keynote speaker at our 8th International Conference on Applied Engineering. Welcome. Voy a dejar entonces ahora como moderador de la sala, nos va a acompañar el doctor Jendrek Velázquez, en quien dejo la palabra para esta conferencia.
Muchas gracias, William. Good morning, good afternoon, and good night, everyone. On behalf of Technical University of Manabí and the Faculty of Engineering and Applied Science, it is a great honor to welcome you all to this academic session within the framework of the VIII International Scientific Convention. Today, we have the distinct privilege of hosting Dr. Singla, an estimate research from the Institute of System Genetics of West China Hospital and Sichuan University on the People Republic of China. Dr. Rajeev is internationally recognized for his outstanding contributions in the field of natural products, also in metabolic disorders and neurological diseases, cheminformatics, and public health. He is founder and editor-in-chief of the Indo-Global Journal of Pharmaceutical Science and serves as an associate editor for prestigious journals such as Journal of Alzheimer's Disease, Frontier of Pharmacology, and Frontiers in Nutrition. He is also a member of several editorials and advisor boards, including BMC Complementary Medicine and Therapies and CNS and Neurological Disorders and Drug Targets. Also, Dr. Singla is ranked among the top of 2% of the world's most influential scientists, according to the assessment by the Stanford University, Scopus, and Elsevier. Throughout his career, he has published more than 150 scientific papers in high-impact journals and also collaborated with over than 780 researchers from 40 countries, reflecting his strong commitment to collaborate science and global scientific communication. It is a truly honor for our institution to welcome such a distinguished scholar whose scientific achievement and dedication serve as an inspiration for future generations of scientists and, in this case, biotechnology engineers. On the behalf of the Technical University of Manabí and the Faculty of Engineering and Applied Science, we extend you our deepest gratitude for your participation in this conversation. Just say, Dr. Rajeev, welcome to the Technical University, and I'll let you the speech right now and the presentation. Thank you for being here.
Thank you so very much. Good morning to one and all. And first of all, I would like to thank all the organizers for giving me this opportunity to interact with all of you. So before taking much time, let me start my talk. So today I'm going to talk about combined approach of two-dimensional QSAR and three-dimensional QSAR machine learning techniques for the design of two pyrazolines as inhibitors of Entamoeba histolytica. So Entamoeba histolytica is it's a protozoal disease. It's a parasite and it causes amoebiasis. So basically, the main reason for its transmission is poor sanitation, and it affects around 50 million people worldwide, and it is responsible for over 100,000 deaths per year. It is one of the third most common cause of death from the parasitic diseases. And the major affected countries from it is India, Italy, Saudi Arabia, Iran, Poland, and Bangladesh. Not only them, even industrialized countries, and they are, because they have the risk groups, including men having sex with men, travelers, recent immigrants, they are also prone to this infection from Entamoeba histolytica. As of now, metronidazole as the main line of treatment for this to kill Entamoeba histolytica. But because of the mutagenic and serious side effects, and because of the resistance, we need to find a good alternative against Entamoeba histolytica. So pyrazolines are being considered as potent anti-Entamoeba histolytica agents. So my purpose is to basically design and develop a model so that we can have a better prediction model, and we can design and develop a more potent agents against Entamoeba histolytica. Even in China, there is a severe cases and there is a strong presence of Entamoeba histolytica infections. The seropositivity of Entamoeba histolytica in Sichuan, Guizhou, and Xinjiang province, they are higher than that in Beijing. There was a study when there is around 1,300 serum samples have been tested, and out of that, 11% were seropositive with Entamoeba histolytica. Even in a case study when there is around 600 men having a sex with men, out of that, 41% of them were having a seropositive with Entamoeba histolytica, and there is a high seroprevalence in Beijing and Tianjin with MSM cases. So why we pick this project? Why we pick to develop a 2D and 3D QSAR based machine learning technique? Because as of now, there is no machine learning based model using a big database. There are few small database based QSAR model, but there is no big database based QSAR based machine learning model so far. So what actually this QSAR model is? QSAR is quantitative structure activity relationship. So it is basically a mathematical model which is based on your experimental data and your computational molecular descriptors. So what happens, like we do experiments in the laboratories, and we have the experimental data with us. Using some computational tools, we can build up the molecular descriptors. Even not only from the purchase softwares, we can even create the molecular descriptors even using the Python RDKit and all, which is freely available. So when we correlate experimental activity with the molecular descriptor, we are able to build QSPR and QSAR model. QSPR is quantitative structure property relationship, and QSAR is quantitative structure activity relationship. So once you have that model with you, then you can hypothetically create any new structure. Basically, you can virtually design a new structure. Using the tools, you can create molecular descriptor, then fit those molecular descriptors in that mathematical model, and then you can predict activity for that hypothetical structure. If the activity is predicted activity is good, you can further proceed to synthesize it and to screen it for that particular activity. Because when you basically it is a high throughput screening where it can help you to filter out the bad molecules, and you can do only the studies with the good molecules. So initially, I have received a funding from Government of India, and that is where I have started this project, and which we are continuing till now even. So we have taken a data set of around 246 test molecules based on pyrazoline scaffold, and they have a very strong and potential activity against Entamoeba histolytica. Then we have used response surface methodology, RSM methodology, that is basically a three-dimensional methodology to define and optimize the parameters which we need to develop the reliable QSAR model. Then, because when we talk about the drug resistance, then one of the key reasons for drug resistance is the presence of P-glycoprotein, PGP protein, which lead to the drug efflux. And because of the drug reflux, we can observe the drug resistance. But there is no PDB protein, PDP of this P-glycoprotein. So we have developed the homology model of it. And then we have virtually docked those molecules with this homology model. Apart from that, we have also performed the prediction. We have also predicted the drug metabolism, pharmacokinetic, and toxicological endpoints of these anti-Entamoeba histolytica agents. We have done prediction not only with the experimental based molecules, but also with the molecules which we have hypothetically designed. So there are various softwares which we have used during this whole study. One of the most important software which we have carried out is VLife Molecular Design Suite, MDS 4.4 version, that we have used for 2D QSCR, 3D QSCR, homology modeling, and molecular docking studies. We have used Minitab and Design Expert for the response surface methodology. We have used Stardot software for drug metabolism and pharmacokinetic, Direct Nexus for toxicity prediction, ChemDraw Ultra for the structure design, and even we have used Python, RDKit, Anaconda, and Matplot and other libraries for the next level of machine learning QSR models. So these are the from the literature. These are the around 16 papers from where we have extracted these 246 molecule data set, and then we have processed these 246 molecules into the machine learning model. Now, why we have selected and curated this database? Because this database has a range of different set of activity. Like the majority of the compound, around 190 compounds, they have a very potential activity of 0.1 to 5 micromolar, which is quite good as a potent agent against anti-amoeba histolytica. Then the range is varying from 5 to 10, then 10 to 15, and so on till 25. So we have a good range distribution of the data set with a higher percentage of the molecules which are more potential. So in the first step, we have designed and developed the two-dimensional QSCR model. So for the two-dimensional QSCR model, we have initially draw all these 246 molecules using ChemDraw Ultra software. Then we have exported them to the VLife molecular design suite. And then we have converted IC50 value. First, we converted IC50 value in micromolar, and then we converted that into the inverse logarithm of IC50 value, which is we also call TIC50 value. The reason for doing it because the IC50 value, as we can see here, the range is very high from 0.1 to 25. So converting them into PIC50 value will narrow down the data points, and then the distribution will be more linear. So it helps us to correlate it in a better way. So then we have for the molecules which we have exported to the molecular design suite, we have done the energy minimization. Energy minimization has been done on different steps. First, for the molecules which are not the metal complexes, for them we have used Merck molecular force field, and initially we have done numerical gradient time, and then we have done analytical type of energy minimization. For palladium complex, we have used UFF force field, not the MMF, because they are more complex. So MMF was not reasonable for them. So we have used UFF initially for them. And then we, after UFF, we move to MMFF in them. A total of 285 variable descriptors has been obtained. And then negative inverse logarithm of IC50 value, we have kept them as a dependent variable and rest of them as an independent variable. For training and test set, we have used all the three kind of options available. Like we have manually curated, we have done the sphere exclusion, we have also done the random selection method. And there are various filters which we have optimized while building the two-dimensional QSA model, and different parameters which we have taken different permutation and combinations are cross correlation limit, F-test in and out, number of variables, selection criteria, variance cutoff, number of random iterations, and number of groups for cross validation. Then initially, before going forward, we need to first understand the why we are using a different set of parameters for the mathematical model. When we perform the response surface methodology for the optimization, we have understand the correlations between different factors. Like initially here, you can see the correlation of variance cutoff and cross correlation limit with the R-square value. We can see that as the variance cutoff is increasing, and as the cross correlation limit is increasing, the R-square value is getting improved. So based considering all these parameters, we have done different set of optimizations. And then we find out a mathematical model which we have given a name of ENT018. This mathematical model, in this data mathematical model, we have manually selected the training set. It is not based on the auto selection by the software. We have manually selected which molecules we need to put them as a for the training set, and we have used this model, which is random selection model with 80% of random selection, as a template, and based on those understanding, we have manually curated it. Then stepwise forward backward with a cross correlation limit of 0.95 with a variable of these, and with all these criteria, we build this ENT018 model. And this is the mathematical equation for this, which we get as the output from the QSAR model ENT018. Basically, when we talk about QSAR is nothing but when the biological activity is directly proportional to the physicochemical parameters. So here, inverse logarithm of IC50 value, which is PIC50, it is the biological property, and these are the different parameters, the molecular parameters of that chemical structure. And here, this is the relationship which is defining and which is varying according to their variation, the activity is getting changed. So this particular model is having a very good R square value, which is around 0.81 with a good Q square value. Yeah. So these are the different fitness plus and contributory chart for these this model. But there is another model which is ENT036 model. Okay, and that model is not actually, if we only look at the R square value, then this model, because this model is having an R square value is 0.49, whereas the earlier model was having an R square value of 0.8. So if we just look at the statistical parameters, then definitely ENT036 is not a better model as compared to that of ENT018. But this is where we have introduced a new concept, which is called prediction preciseness concept. Because let me give you an example. Whenever we do in vitro and in vivo experiment, we never get the same kind of results. But every time we do in vitro and in vivo experiments, we always consider a plus minus value, standard error value, because we understand that even if we do 3 to 5 times the same experiment, will not get the same kind of result. So there will be a kind of variation which we always accept. Okay, then why not we accept that kind of variation when we talk about the prediction? So that will help us to understand that how much precise that prediction will be. So for example, if we say that the prediction should be highly accurate with only plus minus 0.5 micromolar difference, means your predicted activity and your experimental activity should not have a difference of more than plus minus 0.5 micromolar, then this model is not good. This is only having a 37% of accuracy. But if you are okay that even plus minus 3 micromolar difference is okay for you with the prediction and your experimental, then this model is having 82% of predictability, prediction preciseness. So this is how you can select, and based on that, because there are some studies where the difference should be low, there are some studies where the difference should be high. So based on your experimental knowledge, you can understand, you can say that okay, this much error is okay for me as a prediction model, and it can also help me to design and develop a good molecules. But the exciting thing here is, like, if we compare both these model ENT018 and ENT036 model, only if we only compare the R square value for is better for ENT018. But in case of ENT036, plus minus 3 micromolar difference, there is 84.6% of prediction preciseness. So if you compare these two models, if you only look at the statistical significance, which is given by the using some algorithms, then ENT018 was better. But when we talk about the prediction preciseness, where your prediction and your experimental results could have plus minus 3 micromolar difference, that will be okay for you, then ENT036 model is much better as compared to ENT018. despite the fact that R-square value of ENT036 is nearly half than that of ENT018. So we need to take care of multiple parameters together. Not only the R-square and Q-square value, we need to take multiple parameters in our consideration so that the model could be having a good prediction preciseness, and it will be actually a reliable model. Because what happens most of the time, we build a QSAR model which has a very good R-square value and all, but that model does not have like reliability, because when you do experiments in lab, the lab does not reproduce the same kind of prediction based results. So in the next step, we have performed the three-dimensional based QSAR model. So initially we have two models, which is two-dimensional based, and now this is three-dimensional based. Here we have used the atom-based selection-based alignment for these 246 molecules, and we have generated electrostatic descriptors, steric descriptors, and hydrophobic descriptors. And keeping these parameters in consideration, here we got around 9,360 descriptors because they are three-dimensional, they are in the space. So more data points and more descriptors can be generated three-dimensionally. And out of those 9,360 descriptors, 9,342 descriptors, they are variable, and the rest of them, they are non-variable. So we eliminated those descriptors from it. The same way, PIC50 kept as a dependent, and rest of the descriptor kept as an independent variable. In this case also, we have used all type of methods: random selection, sphere exclusion method, and manual data selection method for training and test set. And there are different filters, same like we have in the two-dimensional cases. We have also have different parameters which we can use, and we can do different type of permutation combination to optimize the reliable QSAR model. When we do the optimization for these modeling, three-dimensional QSAR model, here also we are able to get three-dimensional graph where we can see that the relationship between cross correlation limit and variables for the improvement of Q-square value. Here variance cutoff and cross correlation with the Q-square value and different parameters. Based on all these things, we have optimized the three-dimensional QSAR model, and we find out a three-dimensional QSAR model which is 3D103 model, which was better than other models. And this is manually, this model is manually selected. Here also the training and test set has been manually selected, where we kept a residual value of plus minus 1.5, and we use stepwise forward backward and the number of variables, and these are the parameters for it. The model was built on K nearest neighbor, KNN based method. So these are the different descriptors: H2253, hydrophobic position at 2253, electrostatic position at 1814. That is the grid space basically, and this is the range where the results could be better. And in this case, the Q-square value is around 0.69, and Q-square error was also less than it, and predicted R-square value was only 0.2491. So, but here also, when we see the prediction preciseness, this model, when we say only the algorithm-based prediction R-square value, the predicted R-square value was not good. But when we have used our own developed algorithm, which is prediction preciseness algorithm, which we have developed, and that prediction preciseness will help us to understand that with the error of plus minus 3 micromolar, this model is quite reliable with giving a prediction of 82%, 82.52% of prediction preciseness. These are the different grid points, and based on those grid points, the model has been developed. In the third step, we have performed the homology modeling for the P glycoprotein. As I told you that this is the protein which is mainly having a significant contribution in the drug resistance by fluxing the drug out of the cell. So we have for the MDR1 gene based PGP, we have prepared the homology model using the template of mus musculus, and which is having a 57% of identity and 76% of positive with 1% gap. And this is how we have developed that model, and we have given the name of MRPEH1F. And when we compare it for the validation using the Ramachandran plot analysis and other parameters, this model was quite uh, suitable for the prediction. Then we have done the molecular docking study using this model and the other 246 molecules that we have and other designed virtually developed molecule, virtually designed molecules which we have designed. We have used all those and then we have performed the molecular docking, and based on that we have improved our understanding of the different mechanistic sites for and the active site residues in this homology model protein. In the next stage, we have done the ADME predictions. And when we talk about the ADME predictions, there are various parameters which we have taken into account, including the log solubility and log P value, which is a very common thing. Apart from that, we have also taken HERG P for HERG inhibition, HERG PIC50 value. HERG is basically human ether go-to-go gene, which is responsible for the cardiac arrhythmia. Most of the drugs which are clinically used initially, but then they are out of the market, is one of the key reasons for some of the drugs to check out from the market is because of the HERG inhibition. Okay, so this is one of the another parameter which is being introduced for the prediction, and there should not be high level of HERG inhibition. And here also we can see that if we do the correlation between the cytochrome P452C9 pKi value and the IC50 value, there is quite a strong correlation here, because like with the higher 2C9 pKi value, the IC50 value is also getting lower because the red indicate the lower part of IC50 value. Then we have used some glowing concept to understand the structural parameters which are responsible for that particular physicochemical property, like your solubility. So the blue color will indicate that the part of the structure which is responsible for the decrease of that activity, and the red color will indicate the part which will improve that particular parameter. So here these aromatic rings, they led to the decrease in the solubility. It's very common, everybody know it, and even like the aliphatic rings also, they are responsible for the decrease in solubility. But the same way, this part, they are responsible for the increase in hydrophobicity. So according to these, we can tailor down our structure. For example, here this is the HERG inhibition. Okay, we know that this part in this structure, they are responsible for the HERG inhibition. So using the molecular docking and other techniques, we can see that which is the functional group responsible and binding with the active site residue, and which is the functional group which is responsible for these type of HERG inhibition. Accordingly, we can tailor down so that the HERG inhibition can come down, and the activity can be improved. Then this is the lability of against the cytochrome P453A4. The red color indicates the part which is highly labile, and the blue color indicates the part which is not that labile. So here we can see that this N part, this nitrogen part in this structure, they are responsible for more metabolism. They are more metabolically susceptible. So that kind of adduct will be formed when this molecule will get and bind with the cytochrome P453A4 isoform. So based on all these understanding, we are showcasing here 4 molecules which we have virtually designed. They have not been synthesized, they are virtually designed molecules. And as I told you, that QSAR model can help us to predict the activity for any virtually designed molecule. So I'm just giving you some examples here. Like for these 4 molecules, the 2-dimensional QSAR model is giving these prediction for these molecules. And we can see that this C molecule is having a very good IC50 value, predicted IC50 value. When we compare the 3-dimensional QSAR also, in 3-dimensional QSAR also, this molecule was the best one. So overall mean also, lead 153C molecule is the best virtually designed molecule, which was having a better IC50 value than the existing molecule so far. But the same time, as we know that already we have metronidazole with us. But what is the key reason why we are not like promoting metronidazole is because metronidazole is mutagenic in nature. Okay, and this C molecule is also having a susceptibility for having a mutagenicity. So there is no purpose so moving forward with this prediction molecule. Rather than that, we can go ahead with the molecule A, where it is non-mutagenic. So it was having a good prediction with the predicted activity, and it is also non-mutagenic. So we are further working out to synthesize this molecule, and then we'll evaluate its activity. Then this part, if we summarize and conclude this part, then here we have built a reliable two-dimensional QSAR model and three-dimensional QSAR models with a data set of 246 molecules. Then we have also choose to go ahead with the mean prediction value so that we can have a more better accurate predictions. We have built homology model MRPEH1F, and we have performed molecular docking to find the functional groups and the pharmacophoric scaffolds and active site residues. Then combining all these parameters, we have analyzed and understand, and then we are carrying forward with some of the design molecules here. Then this is the next stage of the machine learning based QSAR model, which we are not showcasing here more because we are still working out. But let me give you a little glimpse of it. Like we have used different type of machine learning methods and even deep neural network methods. Some of these methods are here, and if we follow the same kind of just a second, if we follow the same kind of error value plus minus 3 micromolar, then this model, which is XGBoost model, this is having 97.97% of prediction capability. So if we compare with the software based, because initially the three models which we have shown, the 2D and 3D model, they are based on the software, which is V Life Sciences software. But these models which we have built using the Python, Anaconda, RDKit, and Matplotlib, all the freely available version, and we are able to get even a better prediction preciseness as compared to the paid softwares. But we are not comparing here, and we are not showcasing it in that way. But what I mean to say is that XGBoost model was given here is the better prediction preciseness reliability as compared to the earlier KNN based method. And when we perform the cross validation also, in case of this XGBoost model, this is having a prediction preciseness reliability of around 78% prediction preciseness. Though this particular model, this trial 4 model, is not the best one with the 97, but this is also having 92% reliability. So if we compare both, like where we can have the best cross validation and where we have the good reliability, so we are moving forward with the XGBoost, and now we are also doing some other machine learning based deep neural network based models which we are not showcasing here. Then we are also doing some explainable machine learning QSAR, where we are getting the features which are responsible and what is the uh, parameters for that. For example, this is the shape analysis for it. And here we can see that this mole log p value, based on all these model data set and all, like here you can see that this is the feature value where red color is indicating the high feature value and blue color will indicate the low feature value. So these are the parameters which are highly quite valuable for the increase of the for the better prediction and better better PIC 50 value. So yes. We are also building some interface which we are not showcasing here, where we are building the Python based interface model which is GUI interface there, and where any molecule which we entered using either the PubChem ID or the Smile or Campbell or anything, it will be automatically give you the prediction for that. So we are in process of building those platforms now. So I would like to acknowledge for all these research, because there are many people who are behind and helping me throughout my scientific journey. First of all, I would like to thanks my professor and mentor here in West China Hospital, Professor Barenshan, Professor Atanas from Austria, Professor Humberto from Spain, Professor Thomas from Germany, and Professor Michael Heinrich from UK, Professor Ashok Dubey, who was also my PhD supervisor from India, Professor Jesus from Spain, Professor Mohammed from Australia, and Professor Tapan from India, and Professor Javier from Chile. I would also like to thank the funding agencies for giving me fundings to do research. As of now, I would also like to thank my collaborators around the world. As of now, I am working with and published with around 800 authors with whom I have published so far my research and other projects. So these are some of the countries with whom I am actively collaborating, and I'm always open for good collaborations. So because I'm also part of European Society of Clinical Microbiology and Infectious Disease estimate, which is known for creating guidelines for the infectious agents, and I'm representing China as a local champion. And so I would like to invite you all to be the member of estimate, because it is quite helpful not only to understand about if you are working in the field of infectious diseases. Definitely estimate is one of the group which you should join, because they are quite active, and they are quite helpful and open to include more and more people, and they always welcome good discussions there. So if you be the member, there are a lot of benefits. So, and even you can join some projects. In fact, if you be the member, you can even apply for the estimate grants and all. So they will help you to give some fundings also. So this is the scan code which you can use. So me being the chief editor of Indo-Global Journal of Pharmaceutical Sciences, I will also like to invite you all to contribute and to participate in our journal. If you would like to be the reviewer and editor, you are most welcome to approach me. And if you are willing to submit, you can scan the code, and then you can go through the journal and register yourself and then submit the manuscript. You can, I'm all over there on the social media and professional media. So you can reach to me through any platform wherever you like. So even I'm there on the Facebook and other platform, but though I have not shown it there because I'm using them more for the fun purpose. So thank you, and Sheshe, thank you so very much for giving this opportunity again.
Dr. Rajeev. Right now, I'm going to speak in Spanish to the crowd, and then I go back to you to start with the round of questions, okay?
Yeah, sure.
Ya. Hola a todos, muchas gracias por participar en la conferencia del Dr. Rajeev. Como pudieron observar, él lo que hace es integrar toda la información que justamente ciertas estructuras nos pueden dar y predecir de forma acelerada y con recursos, predecir la actividad de ciertos compuestos que pueden tener contra ciertas enfermedades. De igual manera, se pueden optimizar compuestos partiendo de lo que es la integración de la inteligencia artificial, solamente conociendo ciertos datos estructurales. Esto no solamente es utilizable para lo que es, en este caso, la parte clínica, la parte biotecnológica, la parte de alimentos, la parte de ingeniería química, sino también puede ser extrapolado hacia las diferentes ramas de la ciencia, ya que todo nos da una serie de datos que pueden ser utilizados para predecir comportamientos, ya sea, por ejemplo, en la rama de la ingeniería civil o en la rama de la ingeniería industrial. Entonces, esto más que todo es una aplicabilidad que pueden tener las técnicas de aprendizaje automático, en este caso Machine Learning, para poder simular escenarios que a futuro pueden reducir costos, tiempos y acelerar beneficios también. Entonces, esto es más que todo para que tengan una idea, ¿ya? Ahora voy a pasar a lo que es la ronda de preguntas. Por un lado, vamos a tener el chat que va a servir para poder leer las preguntas. Voy a estar trabajando con el doctor Rajeev en lo que es las preguntas para el doctor Rajeev, y los que están alzando la mano pues pueden ahorita abrir los micrófonos para que puedan ir haciendo sus preguntas. Entonces vamos a ir haciendo preguntas por audio y después leyendo las preguntas aquí por el chat, ¿vale? So,
Sí.
Dr. Rajeev, we will start with the round of questions. I was telling them
Sure.
that we are going to open the microphones to the people that is handed, and also we were reading the questions, or also you can read the questions in the chat. as you wanted. Well, right now we will start the round of questions, and thank you very much for your presentation, your outstanding presentation. Also, I have too many questions to you that later I will tell you because I want to integrate some parts of your investigation to mine. So let's start with the round of questions. ¿Quién puede abrirme para que los chicos puedan participar?
Good morning.
Listo. Una a la vez.
Donovan, Duval Donovan abrió el micrófono. Adelante.
Yeah. Hi, my name is Donovan. Nice to meet you. First of all, thank you for the presentation at our university. We really appreciate it. It is a topic with a great potential for the care of the vulnerable places, such a native town in Latin American. And the question is based of that. How can this computational modeling approach, such as 2D and 3D QSAR techniques, be applied to decide mainly natural or also synthetic inhibitors against protozoan pathogens adapted to the warm, humid, and temperate rainy transition zones between the regions of Ecuador, which are often ignored in statistics, taking advantage of the biodiversity of these areas as potential source of...
Can you please repeat, because my system got it restarted actually. So can you please repeat your question?
Yeah. Donovan,
how can this computational modeling approach, such as 2D and 3D QSAR techniques, be applied to design mainly natural or also synthetic inhibitors against protozoan pathogens adapted to the warm, humid, and temperate rainy transition zones between the regions of Ecuador, which are often ignored in statistics, taking advantage of the biodiversity of these areas as potential source as compounds in biotechnological uses?
Yeah. So first of all, like when we talk about what is the application of these computational models, when you do like for example, if you check the natural products, if you check the synthetic compounds, and when you synthesize those compounds and check those compounds against, and when you do the screening against, when you perform the assay against Entamoeba histolytica, you will definitely not get the good. All the compounds will not be good, right? So, but that will actually cause the...
¿Se salió?
Sí, desconectado.
Sí, se desconectó.
Sí.
Ya le...
Aquí está.
Sí, es.
Come back. Open your microphone, Mr. Rajeev. Open your microphone.
But just a second. Let me change the Wi-Fi also, because
Okay.
just a second. Yeah. So first of all, hello, am I audible?
Yes.
Yeah. So first of all these mathematical models, these prediction model will help you to filter out the compounds. Let's say you have around 20 compounds in your lab, okay, and you want to check like which compound will be the better against the Entamoeba histolytica. So the model will not be biased for synthetic compound or the natural compound. It will work for any kind of compound. But since this particular model, which we have talked right now, it is only based on pyrazoline scaffold. So we have also checked them for other compounds which are non-pyrazoline compounds. For them also, the prediction was having there is a good reliability for prediction, though it was much lesser as compared to if your molecule is having a pyrazoline scaffold. Okay. So right now, this particular mathematical model, these QSAR model are specific to particular set of compounds. So if you are designing, or if your natural compound is having pyrazoline scaffold, and if you put that the parameters of that molecule in that software, then it will help you to understand that what is the predicted activity for that particular compound. And then based on that, you can choose that, okay, this activity is better, so I can go ahead and I can screen it further in the laboratory. So it will help you to save your time. It will help you to save your consumables. Okay, because experiments these days, they are pretty expensive. Okay, so the project which we have shown right now, it is only a part of project. It is part of a major project where we are actually building a big interface where where we are integrating all the PubMed, Campbell, and other databases together, and even if we are integrating with the FDA, SEAERS, where you can get the adverse event, clinically reported adverse events reported. So for all the SMILE molecule, for all the structures which you want to screen, it will give you a good picture about different set of results. Like it will give you the prediction activity, then it will give you the ADME parameter. It will also give you the FDA-based reporting if there is already some adverse effects being reported for that. So there are many things which will help you to actually, based on all those understanding, you can finally think that whether you need to go ahead with that molecule or not. For example, when we virtually designed the molecule, in that I have shown you 4 compounds there. Out of that 4 compound, the C compound was having a better prediction activity in both two-dimensional QSR, in 3-dimensional QSR. So if you just look at the prediction, then we should choose C molecule. But C molecule, because when we check the ADMET and toxicity, then C molecule is also mutagenic in nature. There is a possibility that it could be mutagenic. And if it will be mutagenic, it will fail further. Okay, then if you go ahead with C, it will not be a good thought to go ahead with. So then you can keep all these parameters with you, and then you can select, okay, this particular molecule is good with the ADME, this particular molecule is also good with the toxicity, and this particular molecule is also having a reliable, good predicted activity. So based on all those understanding, you can move forward.